Okay, let's dive right into this. Welcome everyone to today's Explainer, where we are literally decoding the ultimate secret of the digital world. We are taking a really fun journey today, going all the way from the microscopic, low-level way a machine actually thinks, straight up to how you can harness that exact same logic to build your very own games. But hey, before we get to the game design stuff, I want you to think about this question. How exactly does your smartphone store your absolute favorite photos? Seriously, when you swipe through your camera roll and you see this stunning, colorful sunset, what is actually sitting inside the hardware? It's definitely not a tiny painting. It is something entirely different under the hood, and uncovering that mystery is exactly what we're doing today. So here is our roadmap. We're going to start with the secret life of photos, decode light switches in binary, unpack the math, see how that math turns into text and color, and finally, apply it all to Scratch programming.
All right, kicking things off with Section 1, the secret life of photos.
And moving right along to Section 2, light switches and binary bits.
You see, everything your computer does fundamentally boils down to one incredibly simple physical concept. It represents everything as numbers using only zeros and ones. This is the binary number system. The absolute smallest unit of this data is called a bit, which is just short for binary digit. Now I want you to think of a bit exactly like a standard light switch on your wall. Deep inside your processor, there are microscopic electronic switches. When a switch is open, the electricity stops, the light is off, and the computer reads a 0. When the switch is closed, electricity flows, the light is on, and the computer reads a 1. Literally every piece of digital media you consume is just billions of these microscopic light switches flipping on and off.
Of course, one switch by itself, well, that doesn't tell us much. So computers group them together. 8 of these bits grouped together makes 1 byte of data. And from there, we just scale up. When you buy a phone with 64 gigabytes of storage, you are buying billions of bytes. A megabyte is roughly a million bytes. A gigabyte is roughly a billion. And it scales all the way up to zettabytes and yottabytes, which, honestly, are just truly mind-boggling quantities of digital light switches.
Okay, Section 3, decoding the numbers.
So how do we actually translate our human numbers into these digital switches? Well, get this. The math behind this highly modern technology isn't actually modern at all. The binary number system was refined way back in the 17th century by a mathematician named Gottfried Leibniz. That means the foundational logic powering the smartphone in your pocket was figured out hundreds of years before electricity was even widely used. How crazy is that?
Now, what's really interesting about this is the extreme contrast between our human world and the computer's world. We humans use the decimal system, which is base 10. We have 10 symbols, 0 through 9, probably because, we have 10 fingers. Every time we move a digit to the left, it's worth 10 times more. Ones, tens, hundreds. But computers, they use the binary system, which is base 2. They only have 0 and 1. In binary, the digit on the extreme left is called the most significant bit because it holds the highest value, and the one on the far right is the least significant bit.
If you ever want to translate a human decimal number into computer binary, it's actually a super simple process. You just divide your decimal number by 2 repeatedly. You jot down the remainders, which, by the way, will always be either 1 or 0, and then you write those remainders out in reverse order. Boom. That gives you your binary sequence. And to go backwards, from binary to decimal, you just multiply each 1 or 0 by 2's positional power and add them all up. For instance, the binary sequence 101101 translates to 32 plus 8 plus 4 plus 1, which gives us the human number 45. It's like a giant, highly logical puzzle.
Let's look at a concrete example so this clicks. The sequence 10101100 is exactly how a computer sees the number 172. By dividing 172 by 2 repeatedly and noting the remainders, we get this exact sequence of 8 switches. Or, as another really quick example, the number 14 simply becomes 1110. It is incredibly elegant math.
Which brings us to Section 4, text, colors, and sound.
All right, so we have the ones and zeros, but how does that math transform into the rich media we love? Let's start with text. Computers don't natively understand letters. Instead, they use a system called ASCII that assigns a specific number to every single letter. For instance, a lowercase a is assigned the number 97. The computer then translates 97 into the binary sequence 0110001. A B is 98, a C is 99, and so on. Now, while ASCII covered basic English characters, today we use a system called Unicode, which supports over 65,000 characters. That allows computers to read and display virtually every language on Earth using nothing but ones and zeros.
And here is the answer to our initial mystery. Remember the photos? How are they stored? They are actually stored as massive grids of tiny squares called pixels. For a really simple black and white image, a 1 means a black pixel, and a 0 means a white pixel. But for those stunning color photos, computers use the RGB system: red, green, and blue. Every single pixel gets 3 numbers, indicating exactly how much red, green, and blue light to mix together, usually on a scale from 0 to 255. So pure red is 255 red, 0 green, and 0 blue. Pure white is all colors maxed out at 255. When you zoom way, way out from millions of these mathematically colored pixels, you see your beautiful sunset photo.
Sound follows this exact same rule. Real-world sound is just an analog, continuous wave. To get that wave into a computer, an analog-to-digital converter, or ADC, rapidly samples that wave, chopping it up into discrete binary measurements. If you increase the sample rate, meaning how many times per second it measures the wave, and you increase the bit rate, you get much higher audio quality. Though keep in mind it will definitely take up more space on your hard drive.
Let's move to Section 5 and see how this all builds. Bringing logic to Scratch.
Now that we know how data sits passively inside a machine, let's actively command it using the visual logic of Scratch programming. Scratch uses a central stage with an XY coordinate grid, and 0, 0 is right in the center. When you want to move a character, which is called a sprite, with your keyboard, you're essentially sending specific numerical directions to the computer. Pressing the right arrow tells the program to point the sprite at exactly 90 degrees and move 10 steps along the x-axis. Pressing up points it to 0 degrees, left to -90, and down to 180. That physical key press triggers a hard mathematical rule.
So the crucial point here is understanding how to manage all this data dynamically when you're building a game, and that is exactly where variables come in. Variables are literally like empty boxes in the computer's memory that remember values for you, things like a player's score or a countdown timer. In Scratch, you just click Make a Variable. But remember the golden rule of coding: you must assign a value to that empty box before using it. Once you assign it, it can be seamlessly set, changed, and displayed on screen throughout your whole game.
Finally, to make your game run efficiently, you're going to need loops. Instead of writing the exact same instruction 100 times, you just use a loop. A repeat loop executes an action a fixed specific number of times. But a forever loop will just keep going endlessly until you hit the stop button or some specific condition is met. For example, if you set a timer variable to start at 100, you could use a loop to decrease that variable by 1 every single second until it hits 0. It takes all the manual work out of the coding, letting the machine do the heavy lifting for you.
And oh wow, that brings us to the end of our journey. We've seen how open and closed electronic switches represented purely as 1s and 0s translate into complex numbers. We've seen how those numbers magically map to letters, dictate the RGB colors of your photos, digitize real-world sound waves, and even power the directional logic of your own custom games in Scratch. It is all so deeply connected. So I'm going to leave you with this thought. If just 2 numbers can create millions of colors, rich digital sounds, and fully interactive games, what will your switches build tomorrow? Thanks so much for exploring with me today, and I'll catch you in the next explainer.